Hi, everyone. I just did an amazing interview with Carlo Rovelli. The man is like Stephen Hawking plus Albert Einstein reincarnated, and he's so fascinating. Such a European, such an Italian, and such an inspiration to me as an experimentalist that I can have high-level conversations, talk about experiment, talk about philosophy, talk about poetry, talk about our influences and human nature. And to me, these kinds of interviews are what make doing the Into the Impossible podcast all worth it. You're going to learn about his new kind of perspectives on theories of everything, on quantum gravity, on working with Benedict Cumberbatch. How would you like to have your audiobook read by Benedict Cumberbatch, which he did, and just be delighted by this incredible character who's tremendously inventive, creative, and is not afraid of controversy. And I press him, as I do with all my guests. No one gets a free pass on the Into the Impossible podcast. But nevertheless, you're going to enjoy this interview as much as I did. Please do those following things. If you're listening to this on iTunes, please subscribe. Please leave a rating. If you're on Spotify, etc., do a follow. YouTube, do the same. Please do so. It keeps the show going, gets me great guest access like today, and you'll hear about an upcoming project that I hope to involve Carlo with that involves Il Maestro Galileo, and you'll hear about that and much, much more, and get tuned up, teed up, and ready for his upcoming book, which is coming out this spring/summer, depending on where you are. And we will have Carlo back. He had such a good time. He's coming back on. Thank you very much. Now enjoy this blast of a voyage into the impossible.
Any sufficiently advanced technology is indistinguishable from magic.
For everything, there is a season and a time for every purpose under heaven. A time to be born, a time to die, a time to plant, a time to pluck up that which was planted, a time to kill, a time to heal, a time to break down, and a time to build up, a time to weep and a time to laugh, a time to mourn and a time to dance, a time to cast away stones and a time to gather stones together, a time to embrace and a time to refrain from embracing, a time to seek and a time to lose, a time to keep and a time to cast away, a time to rend, a time to sow, a time to keep silence and a time to speak, a time to love and a time to hate, a time for war and a time for peace. Today we're talking with the incomparable Carlo Rovelli, master of time, master of the order of time. Carlo, this that I just read you was written in 2000. Kohelet, very good.
The greatest text humanity has ever written.
I believe it is too. And I actually quoted from it in my book, Losing the Nobel Prize, but also in my thesis. The opening chapter was, better is the end of a thing than the beginning thereof. I want to ask you, do you think that Kohelet influenced the following two people? Isaac Newton, who said, for every action, there's an equal and opposite reaction. And or Arthur C. Clarke, the namesake of this fine institution that I am the co-director of at UC San Diego, who said, for every expert, there's an equal and opposite expert. Did Kohelet, did Ecclesiastes influence these two great minds?
I don't know. Certainly not. But it certainly influenced a lot of thinkers all through humankind.
Indeed. So today we're talking about a lot of things, including emergence of perhaps space-time itself. But before we get there, with one of the guiding lights of modern, not only of modern physics and fundamental theories, but also of the popularization and the entrancement, if such a concept exists, with human beings all over the world, with his popular writing and even his appearances in such vast and diverse projects as Disney movies, as I learned that you were in a Disney movie. Is that right?
I was a Disney character. I was Disney Zayeds. I don't know if there's a verb of that. So there's a little Carlo character there with a Disney face.
If I was in a Disney movie, it would be Pinocchio, because I think.
Well, careful. Pinocchio is the only Italian book that has been translated more than my 7 brief lessons in physics.
Which I know has been translated. Right now it's being translated into the 42nd, 43rd.
44.
Oh,
We'll
really?
get into 44. Yeah.
Wow, unbelievable. Well, I want to talk to you, and this is something I'm springing on you without any notice. I'm sorry, but I am involved in a project to translate this, not to translate this book. This is the dialogue concerning two chief world systems. It was written by a fellow Italian who knew a thing or two about time. That's perhaps one of your great influences, Galileo, El Maestro, the Galileo Galilei, of course. And it turns out, Carlo, that this book has been translated, obviously, many, many times. It has been even published in an ebook, which is hard to find, but it does exist. But no such audiobook of this exists.
Oh.
So what I'm going to propose to you, if you're willing after this interview, is to help me with an Italian colleague of mine just record the foreword in Galileo's voice. We are making the first authorized edition, courtesy of the publisher of the estate of that owns the rights to this book. Not Galileo, but the University of California owns this particular translation. So anyway, I'm going to ask you to read the voice of Galileo when the time comes. Not today.
It's a great honor. I mean, of course, Galileo is it's a myth for everybody doing science, but he's not just one of the fathers of science. Science has many fathers, but one of the great fathers of science. But he's also an incredible writer, and is an inspiration for anybody who wants to write about science. He was writing to in a way that everybody at his time could read his books.
That's right. And I actually quoted from that in a piece I'm doing, a series just kind of on a physicist take on the dialogue. And I noted that he came up not only with concepts in physics, Carlo, as you know, but also concepts in psychology. For example, there's one effect called the Dunning-Kruger effect, which basically I exhibit, which is that you think you know a little bit. And so because you know a little bit, you think you know everything. So Galileo says this. He says, this vain presumption of understanding everything can have no other basis than never understanding anything. For anyone who had experienced just once the perfect understanding of one single thing and had truly tasted how knowledge is accomplished would recognize that of the infinity of truths, he understands nothing. I mean, how beautiful is that?
How true. It resonates that what Newton says at the end of his life, right? That he's like a child in front of the ocean of our ignorance. And you know what? In my popular books, I've noticed something. The people who love my books more are those who know nothing about science or those who know deeply about science. I mean, the scientists. The people who know something about science tend to like my books less because they think they know already.
That's very interesting. I think it is a manifestation of this. I actually learn a great deal, not only how to frame things in a way that was influential on me from your writing, on my own popular science writing, but also understanding new concepts and just the essence of a concept. I mean, let's get to the order of time. We'll get that out of the way. Then we'll get to some. We're going to take a deep dive. My audience is incredibly astute. We had on this summer Lee Smolin, you might have seen. Sabina Hassenfelder, Eric Weinstein, Max Tegmark, Stefan Alexander, and also James Beecham. We went over this. Over 1 million people saw our conversations about theories of everything. I'm going to talk to you about a provocative new idea I have for an experiment of everything. But before we get there, I want to talk about The Order of Time because it is such a lovely book. And it really crystallizes in my mind. I read it, and I listened to the audiobook read by none other than Benedict Cumberbatch. I think I like his name because it has CMB in it, and that's very important. He has a great voice, although he does make a typo.
I listened to him and I said, did I really write this? It's so beautiful.
Well, though one of my kids caught a typo that I'm sure that you didn't make, but I think he did. He calls the process that produces helium from hydrogen in the sun, he calls it fission.
Oh, no, it was my mistake.
Oh, really?
I'm totally stupid. Yeah, I'm totally stupid. When I did catch it, I said, oh, come on. I mean, how can I do it? I confused fusion with fission, which makes no sense at all. I mean, a physicist shouldn't do this stupid thing.
Especially an Italian physicist, Carlo.
Especially an Italian physicist, but I did. So apologies. I mean, it's corrected in the new editions, of course, as soon as I saw it. But it was my being idiot.
Good to know. Well, anyway, it doesn't detract from the enjoyment of that wonderful book. So in that book, you really, if I could summarize it, it's really, an ode to Clausius, et cetera. But why did you come upon this as an idea worthy of your time? You have an incredibly demanding schedule. with this. You're so generous with your time, but it took me a long time to set it up because you're so busy traveling, doing research. How do you decide that a topic is worthy of Carlo Rovelli's time? That is the most precious commodity, some say. I actually disagree with that, and that'll be my next question. But how do you find the time?
Well, it's hard. I wrote a book to explain that time is different than what we think about, but in reality, in our lifetime is this difficult thing we have to juggle with. But the big mystery about time, the big problem about time, I think everybody's puzzled and confused because it's not one. It's many layered problems, the problem about time. So everybody talks about some different aspects of time. And my book, I try to disentangle the various pieces. So I think we make a mistake when we say time is this, or time is in fundamental physics, time is not in fundamental physics, time emerges this way, time emerges that way. That's a mistake. Time is a time of our experience. It's a very structured notion, layered. It has a direction, it has memory, it has a metric, it has a lot of properties that we bundle together in a single notion of time. But in nature, they come from different parts of nature, from thermodynamics, from the Newtonian approximation, from disregarding quantum gravity effect, from our brain, because we remember the past. So the book tries to separate these different aspects of time, and I think then it's much more clear what this complex and mysterious things that time is actually emerges from the complexity of the natural world.
Yeah, I recently reread A Brief History of Time, Stephen Hawking's magnum opus, and an edition that came out just a year or two before he died, the third or fourth edition, and I had never really appreciated it. When I read it when I was 16, I couldn't really understand it. And it was it was beyond my appreciation. And now I come to it with the sophistication of a practicing physicist, a professor of 17 years at UC Cal, San Diego. And the comments that I would make on it was really startling in that it's really a book about God and his feelings about God, which startled and shocked me because he was known, of course, as a devout, practicing atheist most of his life. He wrote many works on that. But actually, the last word of his book is about God. And it's like we would know the mind of God. And he was always kind of mischievous, as you know, and you knew him, of course. But that his main purpose in that book was to present these different arguments, thermodynamic time, psychological time, biological time, and then the notion of time in physics. And I feel that he fell victim to the very same thing that our friend, the maestro, Galileo, fell victim to, which is what we call confirmation bias. I'm certainly used to this as well. But in the book, it's really a polemic about the no boundary proposal, in that he's trying in the 1980s to justify why the no boundary proposal is the right notion of how perhaps the origin of time itself emerges. I guess you can be more precise with your definition, but how time came about, basically cleaving off from this abstract notion of space-time becoming time itself, and that he viewed that as an invalidation of the two main reasons to have God. In other words, God was necessary to create time, and God was necessary to create the universal laws of nature. We'll get into that in a bit, but to Hawking, he could get rid of both of those, and therefore there'd be no need in physics for God. I wonder, why do you think, religion and theology, why do you think it was so important to Hawking, who was an atheist, in that, he wrote one book called A Brief History of Time to obviate the need for a God to create time, but also he wrote another book, The Grand Design, to establish that M theory gives the laws of nature. I assume you don't agree with that. But
I don't.
Yeah. Let me give your take first on the no boundary proposal. Do physicists take this seriously? My belief is that they do not, as a justification of how time itself began. What do you think?
Oh, I think they do.
Oh, really?
I mean, not as a solved problem, but as one of the possible hypotheses, not the only one. If you use loop quantum gravity and you study the same problem, namely what happened at the Big Bang, essentially, So we you know very well, much better than me. We understand the history of our universe pretty well for 13, 14 billion years in the past, but then we don't know what came before. And what came before requires quantum gravity, and quantum gravity has been the job of my life, of course. So to understand what came before, we need a quantum theory of gravity, and like loop quantum gravity is one. And Hawking had a tentative theory of quantum gravity, his Euclidean quantum gravity. So he tried to use it to see what happened. And he came up with Jim Hartle, of course, with this idea that in fact you don't need time to exist before the Big Bang. It's a perfectly valuable idea. I think it's perfectly consistent, it's logical, it's possible, it's a possibility. Is that the only possibility? No. In fact, loop quantum gravity seems to suggest something else. If you write equations, a sort of the quantum gravitational equation, and you run back on time, what you find is a Big Bang. You can continue easily, and you find a previous contracting universe, a big bounce. So that's another possibility. It comes out from loop quantum gravity. It comes out also out from other ideas. We just don't know. I think we are gonna know. I mean, this is a simple scientific problem. Well, simple. It's a difficult scientific problem, but the kind of scientific problem that humankind struggled for a while and then solves. And it's possible that before the Big Bang there was a previous phase. In fact, I tend to favor it right now, but I mean, I've changed mine various times. But it's also possible that time started, what we call time, the cosmological time, started there. There's nothing contradictory in that. There's nothing mysterious. You don't need God for that. In fact, God has nothing to do with that. Let me tell you one thing. There was a beautiful conversation between the guy who first started thinking about this question, which is Lamaître.
Yeah.
Lamaître in French means il maestro, the master.
That's right. Yeah.
But he was a very humble and marvelous scientist, one of great scientists. And he's the one who realized that Einstein theory really predicts a Big Bang and something quantum must happen there. And Dirac. Everybody knows Dirac. Dirac was an atheist. Lemaître was a Catholic priest. Yeah. So obviously a religious person and a believer in a God who creates. The two things being different, but he was both. And there's a beautiful conversation that is it's reported by Dirac himself in a recollection of his conversation with Lemaître, in which Dirac sort of trying to be kind. Dirac was borderline autistic, was not very good in social relations, but trying to be kind to Lemaître, says, well, you did these great things in cosmology. It should be very close to your religious. Cosmology is the closest thing to religion. And Lemaître, the priest, the Catholic, the greatest cosmologist of the early times of cosmology, answer, not at all. Yeah. Cosmology and religion have nothing to do with one another. And then Dirac is surprised and says, so why do you say that? Is there other sciences which are closer to religion? And Lemaître, the Catholic, answers psychology. Okay? And he's a believer. And I think he's totally right. I'm not a believer. I'm an atheist. I'm a serene, happy, without any doubt atheist. But I think he's right. Religion is not a bunch of stupid ideas at all. It's an intense experience that people have. It's a way of looking at the world. But if you want to understand what it has, if you want to understand it in scientific terms, which is possible, you have to look in your brain, how we work, how we think, how we conceptualize. It has nothing to do with what happened 13 billion years ago. That's a scientific question.
Yeah. When I read for the first time that Lemaître's ideas were first tried to be used by the Pope at that time to bolster the creation Genesis 1.
That's true. It's a fantastic story. I mean, the Pope. This is a Pius 12, 9. I forgot. Something like that. He gave some speeches saying, "Oh, the cosmologists have proving God because it's a Big Bang. This confirms the Genesis, and Lemaître, who's a much more intelligent person, ran to Rome and tried to talk the Pope out of that, and he succeeded. In fact, his point was, let's not confuse things. This has nothing to do with. The history of the universe has nothing to do with God. I mean, if there is anything interesting in the Genesis, it has to do with the personal experience of people, with what happened inside people, not the history of the world. And in fact, he convinced the Catholic Church. It's remarkable because other Christian denominations nowadays still try to connect cosmology with theology.
Oh, yeah.
I think it's totally idiot. I mean, the Bible has absolutely nothing to do with what we know about the universe.
Right. I always point out that the the biblical, because I read Hebrew, I read Aramaic, I'm a practicing Jew. I'm not Orthodox, fundamentalist, but I am a practicing Jew. And I don't work on the Sabbath. I take time. And you're right. The most meaningful thing, even from a religious point of view, people should note that there are 35 verses in the Torah, in the Old Testament, as we call it the Torah, that involve plausibly some version of creation or creation of animals or people. So 35 verses out of 35,000 verses, so it's 0.1% of the entire book could be considered about the creation of the universe. And I always say, like, imagine you picked up a book and it was like, the title of the book was like, Great Football Players of 1975. And it's 1,000 pages long. And there's only one page about football players, and the rest it's about the Vietnam War. And you'd be like, this book is not an accurate. It's like the people misconstrue the notion of wisdom and knowledge, in that science means, and you can correct me, I'm sure you know Latin much better than I do, but science means knowledge, not wisdom. And I think they're different things. And I think there's an attempt to reconcile and combine wisdom and knowledge from pure scientific fact. And I think that's a misapplication. And one thing that speaks to...
I don't think it's a misapplication. I think that we should not break our knowledge and our wisdom in pieces. I think we should keep them together. I don't think there are different levels of our thinking the world. I think that that's a mistake. We learn things from science. Science, it's a great tool. Of course, we're humans with humans' concerns. There are a lot of things about ourselves that we don't understand. But what we shouldn't. The mistake it's to mix different parts of our knowledge. I think that our, how would you say, spiritual or whatever, our worldview should be deeply informed by science. We change because of science, because we learn. I mean, when we learn Darwin, when we learn Copernicus, when we learn Einstein or quantum mechanics, we change our view of the world. And I try to talk about in my books about all that. And this changes our view of ourselves also. I don't believe in the ancient wisdom at all. I don't think that we find great wisdom in old books, because old books are old books. What's the good about old books is that a lot of people have been talking about them over and over. So we don't read the book. We read the stratification of commentaries. And if you read the Torah, you know what I mean. And that's interesting. But it's also a lot of, going back to wrong ideas. Yeah. So I think that science is complex, but science can include the science of ourselves.
Yes.
And it can include understanding our values, our emotions, our
morality.
Yes, and our sense of why we live, and namely what we want from ourselves or what we fear. We shouldn't separate wisdom and science. Of course, we should separate what we want in life from the cosmology of the Big Bang. These are two different stories. It's like, it's my furnace broken. That's a problem. It's my girlfriend happy. That's a totally different problem. I mean, I should mix these two problems.
No, right.
But we are the same. And in my science, in my philosophy, in my life, I try to bring things together. I work in loop quantum gravity. It's a very specific problem. It brings to a rethinking of space, a rethinking of time. I want this rethinking to stay together with the way I think about myself.
that in your writing. It is not just in its prose, which is poetic and beautiful, but that is sort of a vector, a delivery mechanism. You know, we're in this age of viruses and so forth, but you can infect, in a good way, the reader with beautiful prose, for he or she may not understand the depths of the science, and actually you give them opportunities to skip ahead, skip back as is necessary. But I guess, you know, the fundamental thing for me is that there is sort of a halo effect. You know, for example, Einstein was asked to be the second prime minister of Israel. Now, the man had very, very Baroque notions about nationalism and so forth. And, you know, because he knew a lot about Brownian motion, and he knew a lot about the photoelectric effect and gravity and time, but you and I both know he had, 7 major discoveries, each worthy of a Nobel Prize.
Yes,
and he had
absolutely.
7 major blunders, each worthy of an Ig Nobel Prize in some sense.
Oh, yes. I wrote a paper on the list of mistakes of Einstein.
Oh, really? I want to link to that afterwards.
Yeah. I could say more than that.
Yeah.
I think Einstein is not one of the, the scientists who have got more right things in his life, at least, after Newton. But he's also, of all the scientists I know, the one who has more mistakes.
Yes, like Babe Ruth,
it's
the famous home
the
run hitter.
Mathematical mistakes, conceptual mistakes, assumptions which are wrong, mistakes that he himself recognized. He changed his mind various times back and forth. Some he corrected, some no. You know what? I think the two things go together.
Yeah.
It's a sign of intelligence, changing your mind. So I tell my string theory friends, change your mind. It's a sign of intelligence.
Yeah, I always ask the question, before I debate with somebody, as Galileo does in this great book. This book is a book about debates. It's a debate between 3 people whose names you can pronounce better than my: Simplicio, Salviati, and Sagredo. And
fantastic. I also wrote a debate with the same characters.
Oh, you did? Oh, you must give it to me. So now you're basically agreeing to be a part of this project to translate Galileo in audio form. Imagine that. Imagine Benedict Cumberbatch reading, Simplicio. I don't know. We'll get some ideas from you, Carlo. But I think you're right. And in America, I don't know if you're familiar from your time spent here, but we have, famous baseball heroes, and one of whom was Babe Ruth, who was one of the greatest players of all time. He could pitch the ball, incredibly fast. He could hit more home runs, but he struck out more than any other player. But he also hit more home runs than any other player. And he's sort of, the Einstein of baseball, I suppose you could say. But what, kind of brings you back to what you said about Lamaître. I mean, this guy is remarkable, Lamaître, because he resisted the insults, the daggers, the barbs of Einstein, who called his misapplication of GR atrocious, despicable. Einstein was brutal to him, and Lamaître was just this happy kind of cherub, and he was just like, okay.
And let me tell you my view of Lamaître. So he went to the Pope and said, "Oh, Pope, you are wrong in trying to connect the Genesis and the Big Bang," and he actually convinced the Pope. Right, the Pope follower, and he went to Einstein when Einstein, as you said, and said, "Einstein, you are wrong." And Lamaître was right. I mean, in the 30s, after Hubble and so on, Einstein changed his idea. So I mean, it's not a thing of nothing. Of the same person going to the Pope and finding it wrong, and the Pope agreeing, and going to Einstein and finding it wrong, and Einstein agreeing. It's quite a achievement. And not only that, the most wonderful things about Lamaître is how humble he was. In the paper, all the credit about the expansion of the universe nowadays goes to
Hubble.
Which of course has played a huge game. But the paper by Lamaître has already the analysis of the first observation of the redshift of the nebulae before Hubble measurement, and has already the Hubble law, essentially. But then something incredible happened. When this paper was translated in English, much later, because it was not in the English literature, he put it in an obscure little journal. He himself took away the part that made clear that he was the first one to read the data correctly, because he said, well, Hubble data are so much better than mine that there's no point in it. So you see, he didn't care. he cared about truth,
Yeah.
not about his own personality. And this is wonderful. I wish scientists would be like that today.
Yeah.
I know some that are like that, some not at all like that.
Let's get into that, because I find it very interesting. I get emails every day, and some people are listening to this podcast, you know, friends of mine that will be listening to this, watching this on YouTube and listening to this on the podcast form. And they'll send me their theories of everything, and they're very earnest. And they'll usually say things like, Professor Keating, I'm sure you got these, Carlo, Einstein was wrong. You know, I know that there's a theory of quantum gravity that he failed to do, but I'm not good at math. So if you help me do it, I'll split the Nobel Prize proceeds. They'll never split the medal with me, but I claim in my book that that's a form of modern day idol worship, in the sense that people worship the Nobel Prize and in fact refer to it so much that it's become sort of a secular religion. But we'll get into that some other time. Anyway, I get these comments, but I never get comments. Boltzmann was wrong. Clausius was wrong. Why is it that Einstein is this target? You know, I think the Italians say, you know, the higher you fly, the easier you are to shoot down, or the revenge is the best dish best served cold. I don't know. But tell me, Carlo, why is this fixation with a man? Why shouldn't it be with the ideas? Why are we always so consumed with taking, you know, Einstein was wrong, or I can do what Einstein didn't do, and I can do, you know, this or that? Why not say, here's an idea, it's for the universe? Why is it the fixation with the man or the woman in some cases?
Well, we're humans. We have our weaknesses. We have our ego and all that stuff. But ideas are more interesting. Let's talk about ideas instead of talking about God and human. And let's think about quantum gravity and loop quantum gravity.
I'm going to talk about gravity. I'm going to see how human you are in this. Okay, so I'm going to say something by a quote. Again, I don't like to venerate people just because they have Nobel Prizes. But the famous Richard Feynman said the following. He said, I don't care how beautiful your theory is, how lovely the math is. If it disagrees with the experiment, it's wrong. And
absolutely.
I want to ask you, in the context of loop quantum gravity, there was a claim that there would be a variability of the speed of light depending on its energy, and it's called dispersion. Its energy would be dependent, its propagation speed, effectively an index of refraction would be color dependent. And that was a prediction of loop quantum gravity. I want to ask.
No, that was a mistake. That was a stage in which the dynamics of loop quantum gravity was not clear and yet. So this is many, many years ago. So at the time, there was only the Hamiltonian formulation. So it was much, much harder to see whether the quantum gravity actually implemented a local Lorentz invariance, which is the one of general relativity, the symmetry of space-time of special relativity. Later on, it became clear, especially with a covariant formulation of quantum gravity. It's called spin foam. It's sort of Feynman sum of geometries in between, which you can do explicitly in loop quantum gravity. It became clear that the theory is locally Lorentz invariant. So it doesn't break Lorentz invariance. Mm-hmm. So there's no preferred reference system, if you want. Yeah. So then the claim disappeared, but that was very good because there were various suggestions at the time, and it prompted an astrophysical research. In fact, a large number of astronomical research for violations of Lorentz invariance, for seeing if in fact one can see a phenomenon that breaks the symmetry of special relativity. And this was successful because nowadays we have a lot of bounds on this effect. So nature seemed to be Lorentz invariant in many phenomena far beyond the Planck scale. So this is one of the examples in which people say there are no experiments in quantum gravity. There are experiments in quantum gravity. That's one. And in fact, there were theories of quantum gravity, like Ojava theory and other theories, which were trying to build the theory itself on a breaking of Lorentz invariance at the Planck scale. And these are largely ruled out. I mean, you never really rule out anything in science. The Popper story is a little bit mythical, but they are very much in difficulty because of these experiences. Loop quantum gravity, on the other hand, its theoretical development has clarified that the dynamics is Lorentz invariant, so there's no breaking of Lorentz invariance expected.
Would there be, you might be aware of a recent discovery using Planck 2018 data, of a observation of evidence or hint or at 2.4 sigma, which sounds less impressive than 99.2% confidence, but they're the same thing, that the universe exhibits cosmic parity violation via Chern-Simons additional term to the electromagnetic Lagrangian. This is by Ichiro Komatsu, who's a friend and colleague, and his colleague, who's also a colleague, Yuto Miyamori, who works on the polar bear experiment with me and my team. But they claim that the photons, cosmic polarization photons, rotate as they travel from the last scattering surface to the Earth. And it made me think of a potential probe that I want to pitch to the Rovelli funding agency, which would be looking for parity violating signatures, or maybe less Baroque than that, just looking for a time of flight difference between vertical polarization of distant sources and horizontal polarized light and their propagation. And when we see them from a gamma ray burst or from a supernova, it's actually not well known. I've had conversations with some of the top supernova physicists, Robert Kirshner, my late colleague Andy Friedman here, about testing Lorentz invariance violation and parity violation using time of arrival from supernova of vertical and horizontal polarization. Is there any test analogous to the speed of light for red and blue photons, for example? Is there any test like I'm proposing that could have some discriminating power for LQG?
I'm not aware of anything specific of that in the literature, but I wouldn't exclude that. Nowadays, if you tell me about breaking Lorentz invariance, everything is possible, but that's not everything possible is interesting. But parity or chirality in nature, we know that nature is chiral, and we know that nature treats left and right differently. And if you remember, loop quantum gravity was born. In fact, the action of loop quantum gravity is not exactly the generativity action. There's another term that has no effect in the classical theory, but has an effect in quantum theory. It's called the Holtz term, with a parameter which goes under the name of Berberine-Milzi parameter, which has the opposite parity, if you want, as an epsilon inside. And the loop quantum gravity was born on a formalism that treats the two opposite chiralities differently. So I wouldn't be surprised if something could happen. I think it's a very interesting direction to explore. It has not been explored sufficient. There are some papers, but I don't think it has explored very much in the literature. Remember Smolin and what's his name, Juan
Magejo.
They were trying to explore something in that direction. They were excited at some point. But the way I understand loop quantum gravity today, loop quantum gravity is the way I understand it, it's a very, it's not a theory of everything.
Yes.
It's not a grandiose thing,
yes,
but it's very well defined. It has very clear Hilbert space, very clear evolution equations. So it's a theory of quantum gravity. We don't know if it is right, because until we make a successful prediction, we cannot say this is right. But I think it proves that a theory of quantum gravity can be written. And it's there. It's finite. There are no ultraviolet divergences. And in it, the way it is, I don't see it chirality breaking, this effect that chirality, this effect that you're saying, but I wouldn't exclude that it might come in.
Yeah.
Exactly, because there's this other term, which is a possible signature.
Yeah, when I want to get to possible tests under the strong gravitational regime of colliding black holes in a minute, but before we get there, I want to take one step back for the audience who may be getting a little bit lost, but probably not, because they're very astute. We've had on Frank Wilczek, Juan Maldacena, Martin Rees. We've had on the top luminaries in this field, and I always ask them, and Sir Roger Penrose has been on 4 times, including after he won his Nobel Prize, and I asked him at that time, in conversation with him about black holes. And here's the following thing. Let me run this by you. I feel like the the quantum gravity argument is sort of this Ouroboros, the snake that eats its tail. It's almost like a tautology in that we say we need a quantum theory of gravity to understand the properties of black holes within their event horizons, near singularities, and strong gravitational fields. We also say we need it to explain the origin of time, if indeed time had an origin in a quantum sense, in a Big Bang, in inflation, something like this. We need to have, now, both of those, as Hawking himself proved for both of those fields, we are fundamentally firewalled off. We can never observe a singularity. We don't believe there are naked singularities. We don't believe we can observe what's inside of an event horizon and get that information out. So it's sort of firewalled off. Conversely, the beginning of the universe, when time, as you point out, how does time pass when time comes into existence in a certain sense? So and Hawking showed that there would be this singularity, along with Penrose, and I asked this of Roger, and I said, so there are these two scenarios. We say we need quantum gravity, and yet we can't observe quantum gravitational effects. What do you say? Is this a tautology? Is there any other reason that we believe we must have a quantum theory of gravity? I mean, who says that we have a quantum theory of gravity? Why do we need it?
No, I disagree. I disagree entirely. And black holes are a good example, because let me tell you what loop quantum gravity predicts about black holes. This is, in fact, the main sort of hard science in which I'm working right now. Last night I was up until very late trying to do and not succeeding to do a calculation exactly.
You got to get time in order.
You got to
get the order of time right.
Right. This is, that book should have been titled "The Disorder of Time." But anyway, that's a different story. If you take the question of loop quantum gravity, this has been done in a number of different ways. I mean, different loop quantum gravity formalism. So it seemed to be pretty solid as a prediction of loop quantum gravity. If you fall into a black hole, you have the equations. You see what happened. You go toward the center. At the center, the curvature increases. So you enter the quantum gravity regime. You do the calculation, and you discover that you continue in a region which has a geometry not of the inside of a black hole, but inside of the white hole. So which is a well-known solution of Einstein equations as well. And if you look at the thing from the outside, the black hole for the outside, what you see is that there is Hawking radiation, so it becomes smaller, 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 smaller. Some point it's very small, so there's a horizon. Mm-hmm. And then when it's sufficiently small, there's a quantum transition, a tunneling effect, that transforms it from a black hole horizon to a white hole horizon. And this is compatible with the classical Einstein theories equations outside. So therefore, now you have a white hole. You've gone through this quantum phases, a tunneling, like the standard quantum tunneling, a particle that goes through a potential wall. It's the same phenomenon. So the black hole has become a white hole. So whatever is inside comes out, and easily comes out. In fact, has to comes out because it is a white hole. Now, are we sure that this is what nature has decided? Well, no, of course, because we're not sure that loop quantum gravity is correct. But that's a scenario, it's a possible scenario, and in fact, I think it's a reasonable scenario. I think that the idea that people have that at the end of the black hole evaporation, a black hole pop, disappears into nothing is silly. Mm. There's no theory that says it disappears into nothing. What it does is to tunnel into a white hole, and inside, you see, a small old black hole, which is a teeny mouth, teeny horizon, but inside is huge. It's a huge thing inside. So you don't disappear into nothing. It passes a quantum region, and then it comes out from the small mouth. Mm. So therefore, we do see the quantum gravity region. Of course, we do see the quantum gravity region. Is whatever comes out. Mm. And there is no reason whatsoever for thinking that is hidden. In other words, the horizons exist. Hawkins once wrote a paper saying there are no black holes. It's sort of boutade, but I think he was playing on the definition of black hole. If you define a black hole as an event horizon, yes, then I don't think there are black holes, because an event horizon is a horizon that survives all the way to infinity. But the horizon don't survive all the way to infinity. There's nothing forever in life. Quantum mechanics changes things. So the horizon of the black hole, the real black holes we see in the sky, it's a trapping horizon. The correct notion that Roger Penrose, also got the Nobel Prize for this, introduced. So it's an horizon. You cannot come out from there, but it's not something that lasts forever, because it's quantum gravity. Right? So when it becomes small, it becomes a white hole. And if you want, a white hole has a singularity in the past, a black hole has a singularity in the future, but singularities are just what happen when you enter in a quantum gravity region in generativity. So you enter into this quantum gravity, there are no singularities. Singularity is just, the theory not being able to continue because something else coming in. And we know what comes in. It's quantum mechanics. So the black hole singularity, it's actually a quantum transition to a white hole singularity, which is just whatever comes out, and then you see what comes out. So the argument is hidden behind an event horizon. I think it's wrong.
So that we won't, right, so that it is possible. Now, are there ways, as you know, probably Sabina Hassenfelder and others, who's been a guest on the show, she claims that this, the Hawking, the information loss paradox, which would be leading to the resulting emission of Hawking radiation or concomitant reorganization, perhaps destruction of it. I've had John Preskill on as well. She calls it one of the greatest hypes in all of science, that this is not really a paradox. And in any case, it's unavoidable, unobservable, because Hawking radiation, it won't occur for, millennia to the millionth power. So how do we go about, again, adhering to Feynman? I asked this of John Preskill. If you're saying, Hawking radiation, you won this bet, okay, but do you really know if you won this bet? Because we won't actually be around to witness these types of phenomena. So Feynman, and by the way,
how do you know?
Well, that we'll witness Hawking radiation. I mean, the timescales are, for a large enough black hole are longer.
How do you know there aren't small black holes?
Well, we don't have any, currently don't have any evidence. I don't know for sure that we don't have.
We didn't have evidence of black holes, big black holes, 20 years ago. It doesn't mean that they didn't exist. It didn't mean that they didn't.
Yeah, I'm not saying that they don't exist. I'm saying the.
This is not a wild speculation. It's just a solution of Einstein equation. I mean, they could very well be there. In fact, there is a lot of work on the possibility that small black holes were produced in the early universe, the primordial universe. You should be I'm sure you know about that, right?
Of course, yeah.
You're closer to your job than mine.
Yeah. No, it's certainly we are, and we think about that.
So it may very well be that there are small black holes in the early universe which were produced. We don't know, because it's a tricky, complicated story, calculation, depending on many details. But it's very plausible, and I think, look. When I was a student, I studied on Steven Weinberg, fantastic book on generativity, which essentially says, come on, black holes don't exist in reality. It's very unlikely that they exist.
He talks about the steady state theory too. Yeah, it's interesting.
No. I mean, he has a chapter on the mathematics. It's completely clear, completely. And then he says, look, to make a black hole, you should squeeze the Earth in a centimeter cube. Come on, this is not going to happen in nature. But nature is more creative than even the Steven Weinberg, who's a great scientist. And in fact, in those years, the first indication that black holes are real were coming out, right? The 70s, the 72, 73, when it's sinus. And now we are totally sure that things in the sky exist, which are well described by the mathematics of generativity of black holes. But we first find the stellar ones, and then to our surprise, we said that they were the galactic one, which in fact we were receiving signals by decades, and we didn't know what they were. And then we find out billions of solar times, and then we find the intermediate ones. I mean, we are discovering new kinds of black holes every day. So I think it's perfectly plausible that there are black holes. I don't know, but it's perfectly plausible that there are black holes produced in the early universe, or even if there was a bounce instead of a big bang from previous phases of the universe. A black hole can easily go through the bounds, and so
that's Hawking. So, those are Hawking points that Sir Roger.
Yeah. This is
although in that case, I did falsify that to him. I mean, the actual publication, and he and I have been over this. He's a good friend of mine. That the Hawking points, again, I felt were another example of confirmation bias rearing its ugly head, because essentially what he did is take the bicep 2 data that we released and just analyzed the maps and show where regions were high, in apparent visual impact. In other words, he looked at these maps and said, oh, they must be points of high B mode concentration. And that was totally not the way that the maps are intended, any more than an artist's conception is intended to give you a perspective of what a black hole looks like. But I feel like, yeah, that is a notion. I want to ask you now about gravity in a strong, or quantum, gravity, LQG, in a strong gravitational field, because it seems to me, I had this conversation with Lenny Susskind about a month or two ago. He believes that the, what he calls the stretched horizon or something is more quantum mechanical than the singularity. In that,
I think it's wrong.
Okay, why?
Because this is in fact the same question you asked me before about the information loss paradox. Let me be a little bit more precise here. I think some of your audience is it's well versed in these things, and we can go a little bit in more detail. The information loss paradox, it actually comes into versions: the naive one and the subtle one. The naive one is, information falls into a black hole, and then the black hole disappears where it is gone. But that's a naive one, and the solution is very simple. It will just come out later on. You go through a quantum gravity region. But then there is a subtle one, which is the one which is being discussed today, and is what everybody really today calls the information loss paradox. And this is the idea that the paradox is not after the end of the evaporation, it's before. Mm-hmm. Okay? And this comes from this argument by Page. In fact, then there was a cleaner version, that when a black hole becomes small, okay, if you believe the Bekenstein idea that the number of states of black hole is limited by the area of its horizon, then there are few possible states of a black hole. Black hole is small now, so it can have few possible states. So therefore, there's not enough room for information inside, because you need a lot of states to hold information. Okay, therefore, when the black hole is become very small, the information that is inside should have already come out. Okay? Mm-hmm. And this is what a lot of people today believe, and I am convinced that this is wrong.
Because of loop quantum gravity? Because loop quantum gravity has...
No, not because of loop quantum gravity. It's a logic. It's a logic point. Yeah. These people have been blinded, and I think they are blinded, by overplaying holography. They fell in love with holography. They found ADF CFT corresponding that somehow seems to be connecting a boundary theory with an internal theory. So they believe holography blindly more than established physics. And holography is not established physics. It's an hypothesis, right? So it's not like saying Einstein, Maxwell equation, Einstein, quantum mechanics, classical mechanics. This is correct within its own domain. Holography is an hypothesis. And it's not a clear hypothesis. It's a vague hypothesis that it can play in different ways. In some sense, it's true, for sure. It's easy to prove. In some sense, it's an hypothesis. In some sense, it's speculation. But now it has become a dogma. Okay? If you take this as a dogma, and that's a mistake, then you think that all the observables are at infinity. All you can say about the world, you can say from outside. So about the black hole, you imagine a black hole as something that, lasts forever, and anything you can measure, it's on the surface, and there's little number of degrees of freedom. But you forget one thing, and that's a key point, that inside this small surface, there can be a huge volume and all sort of possible quantum states inside, information inside. So this is a confusion between two notions of entropy. The entropy that governs my exchanges from the outside with these things is a black hole. Black hole is small, has a small horizon, small area. So its entropy for me, it's limited. But this does not mean that the internal state with whom I can be entangled can't be large. And in fact, it is large. Just go into the equation. Believe generativity, believe quantum mechanics, believe field theory. Field theory tells you that inside there's a huge amount of information. So it's false, and is dictated by this falling in love with holography. It's false that the information comes out before the quantum gravity regime. It's false that the late Hawking quanta must necessarily be entangled with early Hawking quanta, which is what people got enchanted into believing. And if you're enchanted into believing there, you come out with all the nonsense, like the firewalls on the horizon, like this idea that there is some crazy quantum stuff on the horizon. I mean, I'm a relativist. I've spent my life in relativity. There is nothing special happening on the surface of a black hole locally. If you're in a small region, it's a completely natural. If it is special, it's just your perspective. You're sort of there's a little curvature there. You're zooming to a
even in the stretched
reference
horizon,
frame, which is crazy.
Even in what Lenny calls it, he says, the thermal background, the stretched horizon, which is a Planck length above the event horizon, apparently. But he calls it the most quantum of all phenomena. And so it's I agree with you. And I had Juan Maldacena on the show, and I asked him specifically, I said, what is the value of ADS-CFT? It works only in 5 dimensions. We know we don't live in 5 dimensions. I mean, it's one of the few things we do know. And he said, well, the value of it is in part because it teaches us about quantum mechanics. And I said,
it doesn't. It teaches us as an aversion of quantum mechanics that is not the one that might be true in our world.
Yeah.
And if these people are so crazy about this idea, why then don't do a realistic theory? Instead of doing unrealistic theories, which they know they are unrealistic theory, they say it's an unrealistic theory, and they say, yeah, but the true quantum theory of gravity should resemble that the day we're going to find it.
Right.
Well, find it. It might be wrong. It might be ugly. It might be spectacularly beautiful in my eyes. It might have incomplete pieces. I'm not saying it's perfect science,
right.
far from me. But it's a theory. I mean, we know the equation, the fundamental equation. We can write them down, are totally clear. There's no space fundamentals. There's no time. They're quantum space. You can write the transition amplitudes in 4 dimensions. There's no supersymmetry. There's no holography. There is a holography in some sense, in a weak sense. There is a holography, in fact, but it's a weak sense, not in this strong sense. And it allows you to do calculations in quantum gravity. So we do have a quantum theory of gravity. There is a quantum theory of gravity. Perhaps it's wrong. Perhaps I'm going to change my mind. I mean, say, oh, no, this equation don't work. Fine, we'll change them. Einstein changed the equation of general relativity 5 or 6 times before writing the good one. So fine, I mean, just Einstein changed, I'm going to change, everybody should change. But we have a theory which is realistic, which is consistent with quantum mechanics, consistent with general relativity, and there is no information problem. And, Sabine, sometimes I disagree with her. Sometimes I find she has strong mind, a strong opinion, but I think she's totally right. That's another thing she said. She's totally on the point here. It's just hype.
Yeah, and I wonder, why we give into that. And you mentioned, about why don't they do calculations that are practical with ADS-CFT? So I asked Juan exactly that, and he said, well, this paper, that he wanted to talk about is about a humanly traversable wormhole. And so I said,
okay, so that's a reasonable thing.
I said,
and Juan, of all this group, is one of the more reasonables.
Yes, he is. He is extremely. And I asked Kamran Vafa the questions I'll ask.
He's kind.
Yes, I do have his ilk. No, I love Juan. He's incredibly generous, and we have on.
I love him too.
I am an experimentalist, so I look for experiments of everything. I want to know as much information in the limited amount of time I have to pay attention, to do work, to love, to do all the things.
I wish I could do more. I could give you more on that. To find experiments. I mean, my hope is to, before dying, to see a confirmation loop quantum gravity, a support of loop quantum gravity, something coming in. There's a lot of attempt in on the CMB. Okay, try to connect the loop quantum gravity picture of the primordial universe with CMB anomalies, but it's a lot of work. I've not worked on that, but there's a large literature. I am more confident in black holes, and there have been papers on signature on very high energy cosmic rays. Let me give you the gist of the idea here. If a black hole forms in the early universe, let's say after the Big Bang, it traps some very high energy photons inside. It's small enough, it evaporates, it liberates this high energy photon. This high energy photon flies and gets to us. This is one of the primordial high energy photons. If you do the calculation, the spectrum of these things and the distance frequency dependence is very peculiar because of this this phenomenon, and this might leave imprints in their distribution and stuff. That's one idea. There are papers. Will it be done? I don't know. I'm waiting. You probably know that at some point fast radio burst where there was a hope to connect it to the. I mean, I don't know how strong it is. I think I'm less a believer that this could happen, but it's not closed. And then I have my own favorite idea. I wish I could give you, which is dark matter.
How so?
Dark matter. The best picture we have of dark matter right now is that it's something that interacts only gravitationally. It's a sort of powder which has no electromagnetic decent interaction. It's sort of flying around. There is a little bit, so density of roughly inside the galaxies like matter, even a little bit more, but not concentrated in stars. Now, suppose there were these primordial black holes and they have evaporated. They become white holes. And white holes, according to the model we have a very, very long survival time before ending, because all the thing inside should slowly come out. So white holes are little thing. What's the size of a black hole? It's a microgram. Planck scale is a microgram. Yeah. It's huge from the point of view of particle physics. It's very small from the point of view of your point of view. Right. It's just a powder. And how does it interact? Only gravitationally. It's neutral. I mean, this could be a component of dark matter. Mm-hmm. Do I have a way to test it? No, unfortunately. So every time the other components are shut down or lose credibility, like the supersymmetry one. I mean, is there anybody who still believes in supersymmetry on the planet?
I interviewed Sheldon Glashow last year, and I said, in your book, because he wrote a book called Interactions, and he forecasted, where could physics go in the next 10 years? And this was in 1988. And basically nothing had been seen, including proton decay, including, signatures at the superconducting super collider, which was never built, but he didn't know it at the time. And, so I started to ask him, well, does this not mean that supersymmetry is ruled out? And I thought he was one of the foremost opponents of string theory. And he said, no, not at all. And he seemed to be much more sanguine about the, possibility that string theory could be manifest, but not as much as my friend and yours, Kamran Vafa. We'll get to why I say that later on, and I take you into the impossible with the 3 questions that I ask all my guests. Now I'll take a quick break to just implore people, if you're liking this video, this conversation, please leave a thumbs up and subscribe to the channel. Please leave a review or follow me, whatever you have to do. Follow Carlo. He's not super active on Twitter, which explains why he's so active. I'll put up his Twitter handle, why he gets so much done in writing, in physics, etc. But just to go back to the notion of testability, when I talked to Lenny Susskind, by the way, I have on many more theorists than experimentalists, although I have had on Barry Barish and Ray Weiss, speaking of black hole physics, and Kip Thorne has promised me he'll come on one of these days when COVID is over. I think he's just like passing me off, but he's so productive. He says he's so productive, and it echoes a little what you were saying before we started recording. COVID's been great in the sense, it's been tragic for millions around the world, but it's been good for productivity for people like Kip Thorne. He's like, I'm turning down every interview request. I'm working on books. I'm working on papers. It's never been so productive.
I should do that. that.
I'll let you off in a couple minutes. Don't worry, Carlo.
No. Come on. I mean, it's lovely. It's great to talk with you.
Yeah. But I talked to Barry and I talked to Ray Weiss, and I said, what are the exciting things that you can do with future experiments? And they started talking about, you could test quantum gravity. In particular, I wonder from the LQG perspective, is not a black hole, the colliding black hole with 30 solar masses each, is that not the ideal laboratory? In other words, when people say to me, we need the future circular collider, which is going to cost 20 billion euros to build, not to operate, just to...
I'm not a fan of colliders. I mean, I don't want to make a strong point here. I don't know, but for the kind of physics I do, it's not colliders we need. Look, the ruling out of some quantum theory of gravity with breaking Lorentz invariance, the Planck scale, was not done by collider. Right. You mentioned proton decay. Proton decay was a great experiment, right? You ruled out SU5. Yeah. It's an effect at sort of 3 orders of magnitude of the Planck energy, much higher than any collider could even dream to get there. And it was done, a big tank of water and some detectors around. So smashing particles is not the only way. It's a good way, but it's not the only way to test nature. There are other things. I mean, there is cosmology is fantastic, astronomy is fantastic, gravitational wave detection is fantastic. There are a lot of things.
That's what I say.
Let me tell you one thing, because there is a quantum gravity experiment which is being much discussed now in some corner of the community, which can be done in a lab.
Talk about
it. And I think it's extremely solid, it's extremely good. It's not easy to do, but it's not impossible in a few number of years. It's not a quantum gravity experiment that is going to distinguish whether loop quantum gravity is true or whether string theory is true or whatever is true. But it would definitely create a superposition of geometries in the lab. And it's a fantastic experiment. It was suggested by 2 groups at the same time, one in London, Sugato Bose and his collaborators, and Chiara Marletto and Vlatko Vedral in Oxford. And it's a fantastic idea. You take a nanoparticle, you split it in 2, like a Stern-Gerlach. You take another one, you split it in 2. And so you have 4 branches. And in one of these two branches, you have the 2 particles be very, very close. Okay, they're so close by that they affect gravitationally one another. So there is a different phase in the quantum evolution in that particular branch, but not in the others. So you dephase that branch, and when you bring together the 2 particles, they're correlated. They're quantum correlated. So do you create quantum entanglement via a very weak, delicate gravitational interaction? Okay, and if you do that, you can prove that this can only happen if gravity itself, namely geometry itself, is in a quantum superposition.
Yes.
So this will be, in my opinion, solid proof. I bet that the results, if the experiment can be done, the results are going to be positive.
Yeah.
Solid proof that quantum geometry exists, that geometry is not fixed, that you can put geometry in quantum superposition. So you see, quantum gravity experiments are possible. I mean, the astrophysical measurement of the Planck Hall violation of Lorentz invariance, this experiment in the lab. If you want, the non-finding of supersymmetry at CERN, which threw many people in desperation. People, physics is in crisis.
Yes, the tension.
Physics is in crisis. I mean, the physicists like me were rejoicing in it. We spent years and years saying, come on, supersymmetry, who believes that?
A lot of people believe it still. We've had
a lot of people believe it still, but a lot of people believed in Ptolemy system years and 100 years after Copernicus. I don't know. I mean, supersymmetry might be true. It's not ruled out totally, but science doesn't work ruling out things totally. It makes things more plausible or more implausible.
Right. Well, it's the whole consensus is science, proving it by the number of authors on a paper, et cetera, that I object to. Let me ask you a question though, because when Bicep 2 made our announcement in 2014.
Yeah, I remember. I'm sorry.
Yeah, no, it's okay. I mean, we learned more about the universe. We learned about truth.
But we did.
At that time, Lawrence Krauss and Frank Wilczek, had come out with a paper that said we have, proved quantum gravity, evidence for quantum gravity in the inflaton, in the quantization of gravitational waves. And I thought that was nonsensical. I actually told Frank that on the show, and we didn't get into too much detail about it because Bicep 2 turned out to be a non-confirmation, just confirmed, as you know.
Yeah, I thought about that. It's a very good question. Yes. So you're asking me.
Would it be if we were successful?
Suppose we had observed it.
Yes.
Which. The effect might still be there. The fact we haven't observed doesn't mean that doesn't
I'm banking
exist.
on it. I still have a $100 million project behind me.
That's right. So, can we say it's evidence for quantum gravity? I think I would incline in your side. It's a bit stretched.
Yeah. The experiment that you mentioned is, what I call quantum, and I love your next book has a lot to say about this. We'll talk very briefly about it because I want to have you back if you'll be so generous with your time in the future. But the point is, what is quantum? What does it mean? Well, people think about the double slit experiment. People think about, the interference, the reality of phase, Aharonov-Bohm effects, etc. What do you make about these new, kind of conjectures? Sean Carroll has spoken a lot. Your friend Sean Carroll has spoken a lot about, many worlds, and I mean, where do you come down on that? Is there any impact? Because I think ultimately, what I'd love to talk to you about today is get a better understanding of the role of entropy within LQG, in the sense that, I'm a lay person, I'm a simple experimentalist, right? So I only can remember certain bullet points at a time. And what I think about is space-time is quantized at a certain loop scale. There's spin networks, spin foams. I can understand those. I can't do the calculations, but I can understand metaphorically what they mean and physically what they mean. I can even think about tests, as I've already described, and how we could perhaps measure it. But things like when you talk about holography and so forth, I would have thought you would be a proponent of it, because at some level, don't you say that there is a fundamental unit of quantum area, of volume, of pixels, of voxels in LQC, in LQG? How does it work? Is that not the most quantum manifestation of quantum mechanics there is? Space-time itself is quantized.
Yes. Well, first of all, you're not a simple experimentalist. You're a great experimentalist. So
Thank you.
That's the main result of loop quantum gravity. Not an input, it's not an assumption, it's a result. I am I don't believe that space and time exist as they are. I believe that in a very strange theory, but I'm a very conservative person. I don't believe in a lot of speculations. I think that we should build on what we understand about the world. And if you take general relativity, what we have understood about general relativity, namely that the space-time, the geometry of space-time is the gravitational field. It's the same thing. So we shouldn't think about space and stuff over it. We should think of the gravitational field and the electromagnetic field and the Dirac field and the Young-Mills fields. So that's one thing we know. And the other thing we know is quantum mechanics. Quantum mechanics is incredibly powerful. I mean, it's 100 years that it just comes out right. Maybe one day we'll find it wrong, but it will come. I mean, for the moment, until we find it wrong, we better assume our best bet by far is assume it's right. So if you take the two together, you get loop quantum gravity. Loop quantum gravity is just that. It's a quantum theory of general relativity of space-time, which is the gravitational field. But the gravitational field now is a quantum field. So you can make measurement of the gravitational field and predict what come out. And in quantum mechanics, make measurement and predict what come out means finding the eigenvalues of observables, right? That the energy of the atom, you compute the eigenvalues of the energy. And often they come out discrete. The energy of an hydrogen atom, of a harmonic oscillator, is discrete. The angular momentum of anything rotating is discrete. So if you do this calculation in loop quantum gravity, that's the key calculation in loop quantum gravity, you take you're curious about the geometry of anything. You have this, this piece of this notebook, you want to know the area of the surface. The area depends on the gravitational field. It's something that computes with the gravitational field, which is a quantum field. So the area of this is it's a quantum observable. Space-time is quantum. Yeah. That's the point. You do the calculation and you find discrete eigenvalues. So you find that the area cannot be arbitrarily small. It sits on either zero or it's a very Planck size area, which you can compute, or the next one, is discrete. So this makes space-time not continuous, but discrete, because you cannot zoom arbitrary small. There's no arbitrary small. It doesn't exist in nature. And you have this quanta of space, this elementary grain of space. The volume also is quantized. So you have discrete, you have chunks of volume which can be this big, this big, this big, but not arbitrary small. Okay? And you have to think about the possible quantum states of space-time as this quanta of space, sort of connected to one another. That's a picture of spin networks, that with transition amplitude for one another, and they don't sit in a space. They are space. The space is made by these things here. And this is what explains why loop quantum gravity cures the ultraviolet divergences. Because ultraviolet divergences, they all come from the hypothesis that you use in perturbation theory, that space is continuous all the way down.
Yes.
You have arbitrary high frequency in the theory, but there is no arbitrary high frequency. When you get to the Planck, that's it. But careful, and now I come to your point. Space is quantum, so it's not discrete in the sense in which you take a set of things. It's not discrete in the classical sense. It's not like the lattice when you do lattice QCD. You take a lattice and you say, okay, this is discreteness, is there, is fixed. It's discrete in the quantum sense. Namely, you can have quantum superposition of different discrete space-time. Right? Yeah. In an harmonic oscillator, you have discrete eigenstate of the energy, but the generic quantum state is not any one of these. It's an arbitrary quantum superposition of this. So the quantum states of loop quantum gravity are quantum superposition, arbitrary quantum superposition of these discrete things. That's the true picture. So it's deeply quantum mechanical. And one has to stop at space in the classical sense. One has to think at this quantum state of things. Of course, in the classical limit, when you disregard the quantum gravity effect, you go back to classical general relativity and you get space-time. It's like photons. Photons, we know photons. We used to. When you go to the classical limit of describing many, many photons, there's just a smooth electromagnetic wave on a large scale. So the same here. The Newtonian space, or the Einstein space with curves and bends, is just the approximate description of, at large scale, of particular semi-classical quantum states, which are in reality seen in the quantum superposition of this quantum space.
And so, would you say
this is quantum gravity?
When I think about it, and you have this ode, even in the order of time, to John Wheeler, but it also, I wonder, who would you rather talk to and explain the current status of loop quantum gravity to? Feynman or Wheeler? And keeping in mind they were both heavily, I mean, Wheeler was Feynman's teacher, was he not?
I wish I could talk with either of them. I talked to Wheeler a lot. I had a marvelous, for me, of course, relation with John Wheeler. I mean, he read my first papers on loop quantum gravity. He was enormously excited. He wrote, well, he was excited about everything, was his personality. But he wrote to me marvelous letters. I have in my, I adore him. In my office, there is in Marseille, there is a copy of his letter on the wall. I put it, and I went visiting him. In fact, I'm a relativist, but I did not study on his book, the big Bible on general relativity.
Really?
So no, I did not. I studied on Bob Walder, Weinberg, and so on, many other books, but not his. And when I went to Princeton, he invited me to Princeton to give one of my first talks on loop quantum gravity, and I went there with my little models of discrete space-time done with key rings attached to one another, because I wanted to show a three-dimensional thing which is discrete in the small, but you can. And he was excited like a baby, and he ran and took his book and opened the page of his book in which he has all the key rings attached to one another in a picture for quantum space-time. He loved the early stage of loop quantum gravity. I mean, he was old at that time, but was very enthusiastic. And then I discussed, of course, he had immense influence on me on quantum mechanics also, because the relation of quantum mechanics, we're going to talk about relation of quantum mechanics next time when Elgalan come out. Yes. But it was deeply, deeply influenced by it from bit information, Wheeler ideas. So if I could go back to John Wheeler and tell him how much has loop quantum gravity evolved. Loop quantum gravity is entirely based on his Wheeler intuition. I mean, the form. I think he was a deep thinker, and he has opened up path for thinking on which I and my colleagues have walked.
Yeah.
And my last meeting with him, he was very old, and I visited Princeton, and we were walking outside in the countryside together. He was talking to me. He was very frail and talking very low voice, and I'm a little bit deaf, so I didn't understand what he was saying. I couldn't say every 2 minutes, please talk higher, louder. So I missed several of the things, but it was still great.
Yeah. No, he was famous for so many things and so influential on so much of physics. It's surprising to me that he's not as well known as he should be, but of course that's a game of psychology and politics.
But of course, if I talk with Feynman, it would be fantastic. I mean, Feynman invented all the Feynman.
That's right.
Theory and spin form. It's pure Feynmanology. It's Feynmanology, right?
Yeah.
It's computing transition amplitude by it's not graphs, it's two complexes because they're not particle moving in space. It's a quanta of space evolving. You're summing over evolution of quantum space. That's what spin form is.
Yes.
And the difference is that the quanta of space are connected. So they're not described by points, they're described by graph. So when you evolve a graph, you get a two complex. So the point, the node of the graph, the quantum space are lines, but then the links span surfaces. So you have a sort of bubbly thing. This is the spin form picture. The form comes from this bubbling thing that you get when you evolve the links. And so the space, you have to think about space-time from some quantum state of space to another quantum state of space as a summing over form in between, which you can think at the same time as a Feynmanology of the quantum space and the connection moving, or as Wheeler form. It's the same thing, Wheeler form. Right? Yeah. So things come together in the intuition. And the beauty of that is you do quantum mechanics not in space-time, right? But off space-time in a way which is finite in the ultraviolet. So this is the beauty of blue quantum gravity. I mean, science is step by step, one by one. Okay, we know this, maybe let's make a little step, and it's going to work. This is the way it works, in my opinion. I think the universe is made by real stuff that interact, and these interactions are real. So if you ask me, are the quantum space predicted by loop quantum gravity real? I think, yes, they are. This is a good way of thinking about the universe. These are little chunks of space. I mean, assuming that the theory is right. If the theory is wrong, they're right in the same, they're real in the same sense in which atoms are real. Okay, even if we don't see them.
Right.
But then we have a very good intuition of atoms and molecules, a powerful way of making concrete. This is realism. Realism is develop appropriate intuition for what's there and using it for grasping the reality, which of course is outside our mind.
Yeah, I'm trying to get Gerard at Hooft to come on because he has some recent speculations in this field about, can quantum mechanics be manifestly simulated? In other words, can you, on an ordinary, classical computer made of silicon, can not exotic superconducting materials such as those we use in our lab, qubits, etc., but can you actually simulate it? And if you can't, does that have some implications as to the veracity of whether or not it's possible to ontologically speak about, what is a model of quantum mechanics? So anyway, I'm hoping to have him on. But one of the questions I get, quite frequently with, Garrett Lisi, Eric Weinstein, these kind of multiple divergent, and I had Stephen Wolfram on, he's sort of the most, clearly, I guess what Einstein used to say, marble and wood, or, whatever. There are these different concepts of theories in physics. I classify Stephen Wolfram as a cellular automata. It's kind of like wood. It's a construction. It's something physical. Whereas marble is this pure form that God uses to make sculptures or whatever. And the question of, is there only a theory of everything? Is there only one theory of everything? And I know you've talked about this, like loop quantum gravity is not a theory of everything. For what does that even mean? But it seems to me that loop quantum gravity might have a better ability. And I'll tell you what I mean in this sense. And I'm not flattering you. You know me better than that.
No, please do flatter me. I'm happy.
Okay, yeah, that's I have to flatter, I have to flatter somebody in the hopes vainly that someone will flatter me someday. But Stephen Wolfram, I asked him on the show, I said, do you get, Bell's inequality? Do you get the EPR paradox? Like, it's not a theory of everything in the sense that it's not going to predict all phenomena, but it may have something to say about, he claims it makes testable predictions about black hole, collisions that can propagate at a certain speed, etc. So you say you're not particularly as interested in theories of everything, but it does seem to me, and maybe it's not true, but in loop quantum gravity, wouldn't things like EPR and so forth emerge in a sense? In other words, isn't that built into the fabric of your version of emergent space-time?
Oh, yeah, absolutely. I mean, look, loop quantum gravity is conservative. It's genuine quantum mechanics. It's not trying to replace quantum mechanics with something else. So you have entanglement, obviously. You have entanglement. You have long-distance entanglement. You have EPR. You have all general relativity stuff because you have the classical limit with general relativity. That's some theorems that do that. So let's distinguish a theory like loop quantum gravity, which builds on quantum mechanics and builds on general relativity, and is a quantum mechanical theory, appropriately adapted for general relativity, so times comes in a proper way and so on and so forth, but it's standard quantum mechanics. Let's distinguish this from wild speculations like, behind quantum mechanics there is a classical story like Toft wants, like Wolfram wants, like other people want. I mean, all my wishes for them to succeed, but there are very strong theorems that say that it's impossible to have a local hidden variable theory. So you can do a non-local hidden variable theory. So you can do a classical theory that reproduces the same prediction of quantum mechanics, but it's going to be even more wild than what you started from, because it has things happening here affecting really classically something happening there in an extremely funny way. It has to break Lorentz invariance. So you want to go back to a classical metaphysics, but the price to pay is to deny everything we've learned about the world with classical mechanics, like Lorentz invariance. I mean, why want to do that? I think you have to adapt your metaphysics or your intuition to what you've learned with physics, and not the other way around. You see, it's a little bit like when they all look like me, like Tycho Brahe. Do you remember Tycho Brahe? When Copernicus came out with his story, one of the difficult things to digest, that everything goes around the sun, is that the Earth moves, right? I mean, the Earth, in Copernicus' model, the Earth moves like crazy. I mean, we are going at crazy speed around, rotate, and also around the sun, both. So Tycho Brahe was the great experimentalist who make all this astronomical measurement and then hired Kepler, which was not a bad idea. He came out with his own model, and Tycho model is a third one. It's neither Copernicus nor Ptolemy's. It's Tycho model. And the Earth is not moving, and then around the Earth goes the sun, and everything goes around the sun, right? So it's an attempt to save the advantage of the Copernican revolution, but not moving the Earth. It was completely misleading, right? It's a silly idea. Why was it a silly idea? Because it was trying to conserve an intuition, a pre-Copernican revolution intuition, not willing to give it up. So there's a lot of physicists that try to save a pre-quantum mechanical intuition instead of just give up, believe quantum theory. The world is not, I mean, one of my titles of my books is Reality is Not What It Looks Like. Reality is not the way we used to think. I mean, simultaneity is not well defined. Things are not classical. They're genuinely quantum. We have to understand quantum mechanics, but in its own terms, not by reducing it to classicality. And this is also in a different direction, the quarrel I have, which people who take the wave function, the quantum state, too seriously. Yeah. They want to reinterpret the state as if it was a thing, a classical field, maybe in Hilbert space. Sean Carroll is one of that. Many world people.
Leonard Mlodinow, Hawking's final collaborator. Yes. This one too.
I think it's a mistake. I mean, the quantum state is like the Hamilton-Jacobi equation. It's like a Hamilton-Jacobi function. In fact, the Hamilton-Jacobi function is the limit of the classical limit of the quantum state. So that's what it is. And the Hamilton-Jacobi function is just a tool for computing where we're going to find the particle. But it's not the thing. The thing is a particle.
That's right.
And quantum mechanics is about things, and these things, I think, is the interaction. That's my deep understanding of quantum mechanics. Quantum mechanics tells you how things interacting with one another. It's about the relation between things. And things have property when they interact. And in loop quantum gravity, this applies to space itself. So space is it's a gravitational field. It's a bunch of stuff that interact with something else because this pen interact with all the quantum space around. And the theory tell us how the quantum space act on the pen and how the pen act on the quanta of space and how all these things move together. And that's the story of the world. This relative happening of things well described by equations that we can write down, which are of course probabilistic equations.
Yeah, when I think about that, I think about, well, what can I test? Because one of the poetic things about your book, The Order of Time, is how longing you talk about the taste of a Madeleine, you talk about the sipping of wine and good friends and good company, etc. And it's longing, and I start off the conversation talking about well, time is the most irretrievable asset. Everybody says that. I actually don't believe that. I think innocence is the most perishable of all qualities, because innocence is time bound. I've got a bunch of young kids. I'm blessed to have them. And I look at them and I'm like, I want to preserve their innocence as long as possible, because it's like a ratchet and pull. It never goes backwards. And once you're exposed to something, maybe good, maybe bad, you can never really get back from that.
You know what John Wheeler used to say?
What's that?
Never run after a woman, a bus, or a theory of everything. Because don't worry, there will be always another one coming after a while.
Well, one of my friends is a cowboy or cowgirl, and she says, cow droppings are like men. The older they are, the easier they are to get rid of. So, some of these things are perishable in a certain sense. But before we get to the final questions that I ask everybody on these, I want to talk about a project that I'm interested in, which is modeled after Galileo Galilei. And that I'm calling it Il Saggiatore, or the Assayer. Galileo is one of his little-known books, but to me, it's another example of his genius, of his brilliance, and of his humanity, that he was, subjected to confirmation bias as much as any other physicist in the world. But he also, despite that, had so many great conjectures about the nature of reality, and that was that comets were a phenomenon in the Earth's atmosphere. That was what he believed. And it's really one of the only blunders that he made, besides the fact that the Earth's tides are caused by the by the Earth's motion instead of by the moon. He desperately wanted to prove Copernicus and others.
Well, that's blunder that you're referring to. It's, in fact, if you read the dialogue carefully, scientifically, it's totally wrong.
Yes, it is.
Because so that's the entire dialogue hinges on this argument.
Right.
You know
what he wanted to call it, by the way, Carlo? Do you know what the original title of the book was?
No.
The original title that Galileo chose was On the Flux and Reflux of the Earth's Tides, which, as you just pointed out, is completely incorrect. It has nothing to do with that.
It's completely correct. So the entire point, he wants to prove the Copernican system by arguing that since the Earth goes around the Sun and rotating itself, the oceans are in a sort of non-inertial movement that creates the tides. And if you think for a moment, this means not understanding Galilean invariance.
Yeah. Which is his greatest contribution, relativity, right? He was
Exactly.
But the other thing that makes me want to pursue this project, and the project is basically look at existing data and see if you can get information about unification of forces, rather than saying you have to propose a new experiment that could cost $20 billion. In other words, look at past experiments. And I give the following example. One of Galileo's observations, which he did make, was on the precession of sunspots, which Mario Livio, who you might probably know very well, he claims that Galileo, that's the best evidence for the revolution of the Earth around the sun, is the appearance of those. But he didn't interpret them right, or he didn't emphasize them enough. But my point is not whether he was right or wrong. That's a matter of history, and science, and historians of science can speculate on. But what I want to say is that data existed at his time, and he could have used it to prove his theory better than the theory of the tides, which was completely wrong. I'm asking you, is it possible that there are data that are out there that we can use already to confirm or refute, because you're a good scientist, the veracity of loop quantum gravity, or maybe even of string theory? I mean, you might already say that string theory is not only refutable or falsifiable, as other people who have come on the podcast have said, it's been falsified. So, are there other examples of low energy limits? Take Hertz. Hertz could prove the electromagnetic waves, which later would be the foundation of quantum mechanical waves and matter waves as well. So and gravitational waves.
I'm going to answer. Let me first just correct, because then people are going to quote you. Yeah. I don't want to say that string theory is falsified.
No,
I don't think it's falsified.
I didn't say you did.
No, it could still be true. I think that science doesn't go falsification. I mean, all speculations are not falsified, but they all can be true. What happens is that you pile up sort of Bayesian confirmation of disconfirmation that make things more plausible or less plausible. So, for instance, the non-discovery of supersymmetry at CERN is a heavy disconfirmation, technically in a Bayesian sense, of supersymmetry and therefore string theory. Namely, if we had found supersymmetry, the people doing string theory would have said, you see, we are on the wrong track. It doesn't prove it right, but it's in the right direction. It weights in our direction. The fact of, for this very same reason, in the Bayesian logic of giving credibility to things, the fact of not having found something when most people were expecting it, lowers the confidence level. And that's why many people have moved away from, sort of taking supersymmetry as string theory is a plausible hypothesis about the real structure of nature after the non-discovered supersymmetry. So I would not use falsification. Yeah. I would use disconfirmation in the Bayesian.
No,
case.
I think.
But let me come to your question, because your question is very good. Of course, it's extraordinarily good, and I wish I mean, the answer is obvious. I certainly it's possible. Of course, it's possible, but where? I don't know. I wish I could find something of that sort. I mean, with my students in Marseille, in postdocs and colleagues, we often have just trying to brainstorm. And one thing we have done, for instance, is that think at all the experiments that gave indication about quantum mechanics in the early day of last century. Right? There were so many. I mean, is there anything similar about quantum gravity? Some interference phenomenon, or something we can read in the immense amount of data we have about the universe that could be a hint of that? We've been searching here and there. Interference is a key that we were. I don't know any. If I knew, I would immediately write a paper to Nature and say, look, let's look there. Or I'll call you and say,
yeah, exactly.
Hey, Brian.
Yeah, I point out.
Brian, let's do that.
Yeah, that would be fun to collaborate. But don't give up, because, it's true that we actually discovered, or McKellar has claimed to discover the CMB in 1944 from the observation of certain transitions in cyanogen gas. And that was 20 years before the discovery by Penzias and Wilson of the CMB. So this happens, and there can be data. And actually,
and the big black hole in Sagittarius there were data about it since.
And Galileo discovered Neptune, but he didn't realize that was what he was seeing. He thought it was.
I didn't know. That. He had an observation of Neptune. I didn't know that.
I always say it's too bad, because he could have had a good career. Okay.
Einstein used Mercury anomaly, which of course was in the data before.
Yes.
I mean, he just found a way to
retrodict,
and he got it from Poincaré. Poincaré noticed that. I'm writing a small introductory textbook on general relativity, on the course that I gave in general relativity. And in fact, I realized that for Mercury, it's pretty obvious. I mean, if you I understand how Poincaré got it. If you take just the data of Mercury, the orbital period, and you fold it, the speed of light, c squared, mm-hmm. And you get a dimensional number. This number is exactly of the order of magnitude of the anomaly in the precession. So a posteriori, I mean, it was obvious that it's a relativistic effect. Right? It's a C-square effect. You just read it in the numbers.
Right, yeah.
So if it's a relativistic effect, obviously it's a sort of magnetic effect of the gravitational field. So it's the right thing to test a relativistic theory of gravity.
Interesting. Yeah, when I think about Galileo and Einstein, first of all, Einstein wrote the foreword to this edition, this book, and he calls it one of the greatest books of popular science writing. Of course,
it is.
Yeah,
Absolutely.
he would say that. So I'm hoping to get you involved to read just the foreword by Galileo, where he.
I wish I'd be humbled and honored of doing so.
Okay, it's one of my life's goals. I will talk to you about that after the show. Okay, for now, we're going to finish up because Carlo, when I became an astronomer, I thought I'd be using telescopes all the time, but I really use telecons all the time. I'm always on telecons. I got one in 5 minutes. I want to finish up, if you'll indulge me, with questions I ask all of my guests, ranging from 8 Nobel Prize winners, soon to be 9, all the way up to the humblest of all people that I am humbled to have on my show. I'm so grateful that people like you come on, and I call these the Into the Impossible thrilling 3 questions. And to hear them, you have to subscribe to my mailing list, and I will send them to Carlo. But for those of you who have not signed up for my mailing list at briankeating.com, please do so. You'll get life tips from Jim Simons, the world's smartest billionaire. You'll get Frank Wilczek's questions. You get Avi Loeb. You may have noticed, Carlo, Avi Loeb has a new book out, which we'll talk about some other time, perhaps, about an extraterrestrial intelligence that visited us. Anyway, if you want to hear Carlo's answers, please subscribe to my newsletter, and I will send them to you, the thrilling 3. And these involve, in one sense or another, time, which Carlo is the foremost exponent, proponent, and really just such a lovely book, Carlo. I know you don't need to hear it, or you don't need my opinion about it, my encomium on it, but it was a very touching book, and I was listening to it at the very end of it with my 9-year-old in the car, and he was talking about, wow, that's like, why is this a physics book, Dad? Because he hears me listen to physics books all the time, and it has a lot more fewer equations than those books. Carlo, thank you so much for going into the impossible with me. I hope we can get together in person, maybe here on the sunny Southern California beaches. And I wish you all the best. And until your next book, Eggland, comes out in a few months, we'll have you back on.
Brian, it was great talking to you. Thank you very much for having me.
My pleasure.
Any sufficiently advanced technology is indistinguishable from magic.